October-November 2015, variant 3.1. Question says, in this experiment, you will investigate how the rate of reaction between sodium thiosulfate and hydrochloric acid is affected by the concentration of the acid. When aqueous thiosulfate ions react with hydrogen ions in any acid, a pale yellow precipitate of sulfur is formed. The ionic equation for this reaction is given below. So here in this equation, we can see two aqueous chemicals are added together to form a solid, and sulfur in solid state is pale yellow precipitates. So the rate of this reaction can be determined by measuring the time taken to produce a fixed quantity of sulfur. Fa4 is 0.1 molar sodium thiosulfate and Fa5 is 0.2 molar hydrochloric acid. Apparatus and chemicals given are Fa4 and 5 are aqueous solutions, a 100 cm³ beaker, 50 and 25 cm³ measuring cylinder, a paper insert with a mark, and a stopwatch. Method shows us that we have to perform 3 experiments in a row, and then we have a small space given here for a table to be formed for 4 marks. So now let's perform experiment 1 first. Use a larger measuring cylinder to transfer 40 cm³ of Fa4 into the 100 cm³ beaker. Now let's transfer 40 cm³ of Fa4 using this 50 cm³ measuring cylinder. This is 40 cm³ of Fa4 transferred into 100 cm³ beaker first. Now the next point says rinse the larger measuring cylinder thoroughly with water, then add 30 cm³ of Fa5 to the beaker and start timing immediately. Now, what to do with this timing? Stir the mixture once and place the beaker on the top of printed insert page provided. Look down through the solution in the beaker at the print on the insert. Stop timing as soon as the precipitates of sulfur make the print on the insert invisible. Record the reaction time to nearest second. So let's do it now. Now rinse larger measuring cylinder thoroughly with water. So just fill it twice and discard the water. It's rinsed. And now take Fa5 to 30 cm³ mark. So empty this as much as you can and then take 30 cm³ of Fa5. Now this is 30 cm³ taken. Now as soon as I will pour this solution in the beaker, I will start timing immediately. So for that, what I will do is I will take this stop clock in one hand, and as soon as I will start pouring in, I will start the stopwatch. Start. Now stir it once like this and put on this paper insert. Take the stop clock in your one hand and now start looking through the solution. As soon as this solution makes the insert invisible, I will stop the stop clock. It's gradually getting translucent. Now it's completely opaque. Yes. Record this time now. Time to nearest second in this stop clock right now is 52 seconds. If the last two numbers are less than 50, round it off to the same number, and if they are greater than 50, so round this off to the next number like 53. Least count of stopwatch is 1 second. Why? Because the last two numbers here are not precisely measured. It is not under the human control. Your reaction time is variable every time. Therefore, the last two numbers are not recorded in the time. We take minimum time as second. So nearest second reaction time recorded is 52 seconds. Empty and rinse the 100 centimeter cube beaker. Dry the outside of the beaker, ready for experiment 2. Now let's move on to the next experiment, where rinse the large measuring cylinder, then use it to transfer 40 of Fa4 into 100 centimeter cube beaker. This is the same point as in the previous experiment. 40 of Fa4 in 100 centimeter cube, 40 of Fa4 in 100 centimeter cube. Now use the smaller measuring cylinder to add 10 centimeter cube of distilled water to the beaker. It means now addition of water is making some dilution. Use the same measuring cylinder to add 20 centimeter cube of Fa5 to the mixture in the beaker and start timing immediately. It means now 20 centimeter cube of Fa5 and 10 centimeter cube complementary distilled water, means a total of 30 centimeter cube again, but diluted. Whereas in the last experiment, they have 30 centimeter cube of Fa5 directly. So let's perform this now. And again, we have to do the same thing. We have to record the time to nearest second. So let's do it now. Now rinse this beaker content first. And dry outside of the beaker as much as possible. Inside also. And now let's rinse this measuring cylinder also. Again 40 centimeter cube of Fa4. .40 centimeter cube of Fa4 into the 100 centimeter cube beaker. Now using a smaller measuring cylinder they have given us, and they have given us for 25 centimeter cube. So using smaller measuring cylinder, let's transfer 10 centimeter cube of distilled water. So here is 10 centimeter cube of distilled water I have taken, and this 10 centimeter cube of distilled water is added to this solution. And now we will, using the same measuring cylinder, we will take Fa5, which is 20 centimeter cube. So we will take here 20 centimeter cube of Fa5, and now once we add this Fa5 into this beaker, we will start the timer. As soon as we will transfer this solution, Fa5 20 centimeter cube, we will start this stopwatch. So let's start the stopwatch and stir the solution once and put this over the printed insert. Now let's wait for this printed insert to get invisible. Now it's getting invisible slowly. Still, the mark is seen. And that's it. The mark is completely gone. Now this reading will be taken in seconds, as 1 minute means 60 seconds here, and now this reading in seconds will be considered as 1 minute means 60 seconds here and 62, and round this off to 3, that means 63 seconds is the observation. 63 seconds is the time recorded. Now let's move on to the third experiment, where it says carry out the reaction using 40 centimeter cube of Fa4, again the same 40 centimeter cube of Fa4, but this time 20 centimeter cube of distilled water is added and 10 centimeter cube of Fa5 is used. So let's perform this now. Now as soon as I will add this 20 centimeter cube of Fa5 into this, I will start a stopwatch and I will stir the mixture once and will place on this insert, and we'll look at the time to make this insert invisible. With the normal understanding, we can estimate that we are increasing the volume of water, therefore the solution is getting more diluted. That is why the reaction time will increase, because the reaction rate is getting slower with dilution. So here we can see that it has passed the previous time of 1 minute and 3 seconds, and still it's there. We can see the cross, and now completely gone. So stop the timer. So the reading this time is 1 minute means 60 seconds and then 76 seconds. So the reaction time recorded for third experiment is 76 seconds. Now they have asked you to record all your measurements in the appropriate form in the space below. So the space they have given below is here, where we have to record all these observations. So let's make a table and record all the values. So here I have made a table where I have recorded all the experiment numbers with the volume of Fa4, 5 and distilled water added, and the time taken by those reactions to get completed in seconds. Now let's move on to the next part, which says the rate of reaction can be represented by the formula below. Rate of reaction is equals to 1000 over reaction time. Use this formula to calculate the rate of reaction for experiments 1 and 3. Give the unit. Now, the formula is 1000 over reaction time. And if we look at the previous part, the time for the first experiment was 52 seconds and for the third one it was 76. So we will divide these two with the 1000 to get the rates. So let's divide them now. So 1000 divided by 52 for the first one and 1000 divided by 76 for the third one. In the first one, the value comes 19.23 up to 4 significant figures, and for the third one it is 13.15. Now, if we look at the unit, the formula says 1000 over reaction time, and the time we have calculated in our previous part was in seconds. Therefore, the unit here will be 1000 upon seconds, means second inverse. So for both of these, the units will be per second. The next part says calculate the initial concentrations of hydrochloric acid in the reaction mixture in experiments 1 and 3. Now, if we look at the first page, they have given us the concentration of acid 0.2. But why they have asked you to determine the concentration of experiment number 1 and 3 now? It means the concentration must be changed because you have added a lot of other things. Like if you look at the table, in the first experiment, you have taken 30 centimeter cube of acid and you have added 40 centimeter cube of Fe4 also. So the total volume is now 70. In the second case, you have taken 20 centimeter cube of acid and you have added water and Fe4, making up a total of 70 centimeter cube again. So in all these cases, you have picked up different volumes of acid. So firstly, we have to use these volumes to calculate according to this concentration. The volume and concentration will give you the moles we have picked. And then we will divide it by the total volume of solution, that is 70, to get the concentration. So the formula here is concentration is equals to amount in moles divided by the total volume of mixture in decimeter cube. So in first experiment, experiment 1, how many moles we have picked? Volume we have picked was 30 divided by 1000 and the concentration given is 0.20. So the moles we have picked in the first experiment of acid were 0.006 moles. And now the total volume was 70. So the concentration can be calculated. Concentration is written in a square bracket. So I am writing concentration of HCl in the first experiment is moles over the volume is 70 centimeter cube. So divide by 1000, you will get in decimeter cube. So here if we calculate the concentration, it will be 0.0857 up to 3 significant figures. In the same way, we will do it for experiment number 3. So now for experiment number 3, how many moles we have picked for acid? We have used its 10 centimeter cube. So concentration is 0.20 is equals to moles to be calculated divided by the 10 centimeter cube means divide by 1000 decimeter cube. So the moles we have picked are 0.002. And now these moles are present again in the total mixture 70 centimeter cube. So concentration of HCl in third experiment is 0.002 divided by the total volume, that is 70 over 1000. It means concentration here is 0.02857 means 6 up to 3 significant figures. So again here the concentration is 0.0286, which is lesser than the first one. Obviously we have added more water here. Now let's move on to the next part, which says how is the rate of reaction affected by the concentration of hydrochloric acid in the mixture. Now they have given you the idea in the above parts. If we compare the rate of reaction with the concentration of HCl used, it shows when we have a bigger concentration of acid, the rate is also bigger, or you can say faster. When the concentration is decreased, the rate slow down means it's also decreased. So we can conclude that increasing the concentration of acid is increasing the rate of reaction. So we can say the rate increases with increase in concentration. of hydrochloric acid. Now let's move on to the next part, which says predict how the reaction time measured in experiment 1 would have been affected if the experiment had been carried out using 0.2 molar sulfuric acid instead of 0.2 molar hydrochloric acid. Now, if we look at both the acids, the main difference is H2SO4 sulfuric acid has got 2 H plus ions per mole, and for hydrochloric acid it's just 1 mole of H plus ion per molecule. It means for every mole of these two acids, sulfuric acid is giving you double H plus as compared to HCl. It means if sulfuric acid is giving you higher concentration of H plus in the solution, it means the rate will be, of course, increase. And if we conclude in clear calculations, we can see double. So the rate with H2SO4 is double as compared to the rate of reaction with HCl. Therefore, we can say H2SO4 has 2H plus per molecule as compared to HCl. So rate increases when concentration of H plus doubles. And therefore, because they have asked you how the reaction time would be affected. So therefore, the reaction time, double rate means reaction time will decrease to almost half. Now, moving on to the next part, which says predict how the reaction time measured in experiment 3 would have been affected if the experiment had been carried out in 250 centimeter cube beaker instead of 100 centimeter cube beaker, and explain your answer. Now, if you think in 100 centimeter cube beaker, if we have taken all together 70 centimeter cube, so the volume was up till here by max. And if we take a bigger beaker of 250 centimeter cube, of course, the same volume, 70 centimeter cube volume, will be, of course, in a bit lower depth in a bigger beaker. Therefore, what we were doing, we were actually looking at this cross from the top. Therefore, if we are looking here, the solution's depth is lesser. And if solution's depth is lesser, the visibility of cross will be more. Therefore, the reaction time will increase. So we can say time will increase because the depth of solution in larger beaker will decrease, causing greater visibility of paper insert under the beaker. So here we comes to an end of 9 marks question, in which we have seen effect of concentration on the rate of reaction from October-November 15 variant 3.1.